How is everybody today? How was your weekend? Not too bad?
What about you, sir? What about you?
Yeah. It was okay. It was the 10th anniversary of my mother's death over the weekend, so that was a thing. Wow, that certainly made the room go quiet. It's okay, death is a part of life. You're just gonna have to get used to it eventually. It's kind of interesting when you encounter people, you can kind of like tell pretty quickly by talking to them whether or not they've lost a parent. There's like something about the way they speak, you know? But anyway, there's like a great, they inhabit a more real reality because they've had death in that reality, something like that. Anyway, enough about death. Let's talk about file types that you may or may not find useful on this eventual march into the grave. So we're going to talk about YAML. YAML stands for yet another markup language. So we're going to go through this one reasonably quickly. We've got lots to do, lots to do, lots to do. After this, I'm going to skip, I think, directly into the stuff on databases. So, that will be the way it'll be. So, YAML sort of represents for JSON the same transformation that you might apply to C or Java in order to derive Python. You have a simplification of the syntax. Semantic weight is now put on indentation and new lines, whether things are on new lines or not. That tells you how things are composed inside of the YAML file. And, pardon me. Aside from that, it's pretty straightforward. So YAML is a plain text markup language representing key value pairs and lists the same way as JSON does. It can also support custom data types, however, which is something that JSON does not do. YAML emphasizes human readability and minimal syntax. Human readability. Most commonly used in configuration files and sometimes for data transfer and storage. So essentially, the observation that was made of JSON files is that they're quite useful for making configuration files. However, they're also a pain in the butt to work with because they're, there's just a lot of curly braces, right? And if the path that software languages have taken over the last 10, 15 years tells us anything, it's that people hate semicolons and curly braces, more elegant weapons of a more civilized age. So often, when you find configuration files for various things, one example that's coming up in 1xC3 next semester, we're going to be talking a lot about GitHub, because GitHub is extremely useful. How many people have used GitHub? Excellent. A little bit. Hopefully you will be, even if you've used GitHub somewhat casually, you'll be much better familiarized with its more advanced features by the end of 1xC3, since these are the sorts of things that are actually expected of software developers these days. At any rate, we're going to be talking about a way that you can set GitHub up to run certain programs automatically whenever it receives a commit.
GitHub Actions.
GitHub Actions, yes. and continuous integration testing. GitHub Actions are, the way that you configure the GitHub Actions is write a YAML file. Now, it's not necessarily going to have the YAML extension every time that, every time that it's used. You'll find, that's actually something that's true quite a lot of JSON as well. JSON is a general format, but you will find many things formatted in JSON format that are not explicitly JSON, like file extensions, right? The Jupyter notebooks are an example of that, right? They are .ipyrb, but if you just peel back the surface, it's all JSON underneath. So in the same way, YAML files will not necessarily have the YAML extension, but you should recognize one when you see one. Make sense? YAML is a superset of JSON, thus all JSON files are valid YAML files, but it's another one of these sort of subset, superset relationships. All JSON files are YAML files, not all YAML files are JSON files, right? Make sense? Obviously, JSON requires the curly braces. In YAML, they are optional, so if the YAML file doesn't have the curly braces, it's not a valid JSON. Make sense? So far, so good? Okay, so this is how a YAML file is written. We have key value pairs. Indentation here indicates the nestedness of the data structure. So at the top level here, are we dealing with a list or a dictionary? You should be able to just, yeah, it's a dictionary. Note the colon, right? If you take a Python dictionary, right? Take all the key value pairs, put them on different lines, remove the curly braces and the commas, you end up with YAML, right? Lists. Lists occur as basically bulleted lists, right? It's a hyphen character instead of like a dot or a circle or something you would expect in Microsoft Word. But essentially, it's okay to think of this as being a bulleted list. And whatever level of nesting it's at, that's where it occurs in the file. So, for example, before install, that points to a list containing 2 items, which both have these. These are bash commands, I believe. So, yes. So you can see also that another thing that's conspicuous by its absence is quotation marks. The assumption is broadly made inside of YAML files that if you have a series of characters, it is a string, and you do not need quotation marks to designate strings the same way that you need them inside of JSON files. Make sense? Hopefully. Numbers, of course, are stored as numbers in a native numerical format. And I'm sure that any YAML parser you have will take something like false and convert it to a Boolean if it's just a string false. Stuff like that. Any questions? Should be like a reasonably easy mutation of JSON. So, YAML uses block format or flow format. That's what they call their 2 formatting, and this is how YAML files technically also include JSON files. JSON files are flow format. Flow format allows for curly and square braces to be used to denote maps and lists, like JSON. This is why any valid JSON is a valid YAML. Flow format exists primarily for JSON compatibility, but is less readable. So it is often very useful when you're defining a new format or a new program or something like this. It's often very useful to design it in such a way that old versions still work with no modification, right? Back compatibility. You want to be like the Game Boy Color, which could still run original Game Boy games. The sort of Python-esque version of YAML is called block format. Colon is used for key value pairs or maps. Lists are represented by lines which begin with a hyphen. White space matters. Tabs indicate nesting, and only one value is allowed per line. It allows scalar and custom data types, like JSON. Quotes are not needed for most strings. Cool? Right. Unlike JSON, Python does not have a built-in parsing library for YAML, but one can easily be installed through pip. So pip install PyYAML. PyYAML is the library. Some distributions will come with it, some won't. If anybody is sufficiently hip, maybe you can look up to see if Anaconda comes with PyYAML. Does it not? Okay, so you'll have to install it. Reasonably easy. YAML.safeload or YAML.load loads YAML files into a dictionary, or your standard dictionary list nested structure thing. They can then be used like Python dictionaries or lists, or you can also use them as JSON files. Make sense? Cool. This is a code example. I'm going to skip the actual doing out of this one on my computer because we have material we need to cover before the exam. But if you'd like to give this a more thorough look through, you can do that on your own time. Left as an exercise to the reader. So, Docker is pretty popular these days. Docker is used in countless configuration applications, infrastructure, and web services. So, for example, Amazon Web Services, Nginx, Travis CL, GitHub, etc., all use YAML files for configuration. So, if you have any, I think I heard recently that 40% of all programming jobs are like front-end web development, and 40% of all programming jobs are also back-end web development, something like that. So if you're a web developer, this is not optional knowledge, shall we say, how to use YAML files. Fortunately, they're pretty easy. So, to set configuration in a YAML file, you just go in to the text and you modify it in whatever manner you see fit, and then you rerun whatever it is you're running, and boom, you have your configuration changes. Make sense? Coolio. So that closes out file I/O. Anybody have any questions about file I/O before we move along? Okay. So we'll go right to databases. So, can anybody tell me what a database is? Yes?
It's an organized collection of data.
It's an organized collection of data. Yes. You can think of it as a place where all of the important information is kept. If you are working one of these web development jobs to which I referred, the database will be where you keep things like login credentials, your customer's order history, your inventory of items that you have for sale. All of these types of things are fundamentally stored in databases. Databases have a lot of fancy algorithms that go into their production, which you will talk about more in the second year. For now, all we're interested in doing is providing a sort of gentle introduction to structured query language, which is one language that is used to interface with database software. So, goodness. So, databases, so basically, structured query language is a language. It has syntax and semantics, and while it's not necessarily a compiled language, you do feed these statements of the language one by one into a program, and these constitute manipulations of the database that you are requesting, right? So every line of SQL is something you're asking the database to do or retrieve for you, right? So, like programming languages, databases allow us to process and store data. However, data is stored in dedicated files and loaded as needed. Data can be much larger than the available memory, and there is no need to explicitly open the files and read the data. So how it works is when you open up, when you start up a running instance of the database software, it will grab the file which it's interacting with, and then it will communicate with that file. One of the really important aspects of a database is that it can be accessed, quote, simultaneously by more than one client, and those clients can be either local or remote. We will not be dealing with remote databases in this section of the class. We will be dealing with a piece of software called SQLite, or SQLite, which is it's very similar to, it implements the same language that many of the relational databases you'll find sort of out in industry use. But it operates only on local files on your file system, and therefore it's sort of doesn't require any networking or setting anything up. You kind of just download the program. You can work on a database file without having to worry about, all of the eccentricities of web access. So, data is atomically updated. Data is either stored or not, but never becomes corrupt, even in the case of failure, that is to say disk error or network disconnection. So, you do not, that better be Jesus calling. That's a quote from a movie, by the way. You can imagine the sorts of file I/O that we've been doing so far, right? We open up a file stream, and we are dynamically writing to this file as things progress, right? You might imagine that if your Python process had an exception while you were writing data into the file, right, some or all of the data that you were writing might be lost. This is generally known as corruption, right? With relational databases, each line of SQL that you are sending to the database happens, it receives all of the data it needs to perform that one action at once, right? It performs it, and then it starts the next action, right? By doing it that way, there's no possibility that an interrupted network connection, for example, will result in some of the data that's being sent to the database being lost. Packet authentication and everything else. So, Relational databases structure data in a very specific and particular way. The analogy is to spreadsheets. It works roughly like a spreadsheet. You know, if you take away a lot of the ability to do formulas and that sort of thing. You don't put the formulas in the cells in the spreadsheet, right? If it's a database, you write formulas in SQL and you can store functions and that sort of thing. And that's how you do that sort of advanced calculation. Complex queries can be written in a dedicated query language. So SQL is Turing complete, right? Anybody remember what Turing completeness means? Yes, sir.
It's an infinite computing machine. You can do basically anything you want with it. So it's got the infinite spool of tape and stuff. In practice, it means it can like simulate itself.
Yeah. So, yeah, that's pretty good. It can simulate itself. So, when a language is Turing equivalent, it means that anything that can be computed by any Turing complete language can also be computed by SQL. SQL is a domain-specific language, however. It is designed and optimized for database interaction and database access, which means it's not as efficient for general programming. This is, again, one of the reasons there's no universal programming language. Each programming language is good at different things, right? In this case, interacting with databases. So, data and their relationships are stored in tables. So, in the same way that a spreadsheet has rows, columns, and several sheets, this is roughly the same organization inside of a database. In a database, sheets are tables, rows are records, or objects or entities, and columns are fields, values, or attributes, depending on who you're talking to and what type of terminology they like to use. Make sense? So far, so good? Good. So over the course of this course, we're going to work with a example scenario of a video rental store, a now archaic feature of a forgotten civilization. So essentially, video rental stores used to be stores where you could go and pay a small amount of money to receive on a temporary basis a physical copy of some kind of entertainment media. Sometimes it was movies, sometimes it was video games. Most of the time it was movies, as video games were always more of a niche market. The video rental store itself has been largely superseded by the relentless march of technological progress, and basically actually broadband internet is the thing that killed the video rental store. They still existed well into the dial-up era, because during the dial-up era, it would take a very long time to download something like a movie. Yes?
Sir, video rental stores were up until like 2010. I remember seeing one.
Yeah, but they were not,
They were dying.
yeah, it's kind of like,
I saw a Blockbuster at like a Walmart in, well, not where I live. I saw a Blockbuster in my church. Pretty much everywhere in 2010 as well.
yeah, it's, so basically, you and everybody in this room except me, unless you're like the same age as me, you guys are like living, like historical analogy, you guys are living like at the tail end of the Roman Empire after Rome has been sacked by the Gauls. Sure, you know, the Romans like still exist in theory, but like they are in the process of being decimated by war and plague, and in a century or two, you know, the population of Rome will go from 2 million to 10,000. So, you know, understand that you're in decline. Yes?
Isn't it the Goths, not the Gauls?
The who?
Goths.
Goths? Oh yeah, the Visigoths. Yeah, the Gauls were different. Yeah, thank you. Thank you. Yeah, it was the Visigoths and the Lombards that eventually brought down Rome in the 5th and 6th centuries AD. So, anyway, back when video rental stores used to exist, they had to keep databases of the movies they had available to rent, the customers who would rent them, and which customers have rented which movies, so that you could charge them money when they didn't bring them back on time. Kind of like libraries. Libraries will still perform this function. I'm quite sure that you can still rent physical media from libraries these days. So, we will create a small database containing 3 tables: movies, customers, and rentals. Here is an example of some of the data which we will store in the movies database. We have a table consisting of attributes and records, or shall I call them fields and records, yes. So we have 4 fields here. We have a unique identification number. We have a title, we have a genre, and we have a rating. Reasonably straightforward.
What does PG mean?
It means for parental guidance, but I forget what it like sarcastically means. It's pretty much garbage. G is garbage. This is pretty much garbage. R stands for restricted, but it's, you know, maybe, yeah. Sure. But then all movies are garbage, you know. Then you have PG-13, which is, the analogy kind of breaks down a little. Anyway, so, you'll notice that the data here conform to a regular format, right? For each of these records, we have certain fields defined, and these fields have certain data types defined. Now, I know that you guys have been studying Python, and that the idea of databases might give you nightmares, or the idea of data types might give you nightmares, but in all sane programming languages, you are expected to know what data type things are supposed to be. So, in relational databases, we have the database schema. Each table has a schema associated with it. The schema specifies the names and types of the fields of each table. So, this varies widely by database software vendor, but these five fields will be there in all of them. You know, the particular set of data types that you have available is dependent on which databasing software you're using, but they will all have the ability to store integers, for example. They might call them ints to save space, but you know, it depends again on what you're using. So, for our example table, the schema, we have our movie ID stored as an integer, and then title, genre, and rating are all stored as text. Text being equivalent to strings in this case. Pardon me. So, good. So let's talk about SQL. SQL, or Structured Query Language, is a widely used database query language. It was first proposed in 1974 for COD's relational database data model from 1970. Truly, the 1970s were the time to be a computer programmer. All of the interesting and unique technologies which we are still figuring out how to use, almost all of them were developed during the 1970s. Basically, this was when all of the groundwork was laid, and we've been waiting for technology to catch up to it. And, you know, in the last 10, 15 years, it's more or less caught up to where they had the ideas back in the 70s. But so SQL can be used to interact with a database. That is to say, you can fetch a set of records, add data to a table, modify data, delete data, do all of the sort of standard data manipulation operations that you might expect. Syntax is mostly independent of vendor, but not entirely. SQL also supports transactions like begin, commit, and rollback, authorization, stored functions, and many more additional features. We will be sticking to the basic features for the time being. SQL is more general than the examples suggest. For example, the results of one SQL query can be made the input of another. Recently, no SQL databases for storing differently structured data in cloud storage are becoming popular, but they have become popular, but they are still like, SQL is still sitting on its throne, flicking peanuts at them. So SQL is like industry standard for like a lot of very serious applications like banking and stuff like that. So there are many database programs available, all of which, all of these guys, well, except for that one, a lot of them all use the same language, let's just say. In terms of commercial database software, we have Oracle, Microsoft SQL Server. Boo. We also have open source ones like MySQL and MariaDB, PostgreSQL. Who knows? Yeah, PostgreSQL. Yeah. SQLite, which is the one we'll be using in this class, and MongoDB, which is a non-SQL database. As I mentioned previously, Mongo is actually using JSON in the backend, or something similar to JSON anyway. Apparently this one's like, in recent years, has emerged as one of the clear winners of the sort of online SQL space. Yes?
So does NoSQL mean non-relational?
Yeah, it means that, I'll take Mongo as an example, right? In MongoDB, basically, you're accessing data through a series of map and list accesses, rather than, give me X number of records that all match some filter, right? Like, you can certainly still do filtering, but like, the underlying data structure is a JSON file, and therefore not rectangular, right? Or at least it can be rectangular, but it is not required to be rectangular. Make sense?
I was just thinking of something like Microsoft Access, where you can write queries for it, but they're not in like the SQL language. I don't think they use their own weird Microsoft language.
Hands up everybody who's surprised. Yeah, there's a reason Access isn't listed here. Like databasing is a very, very common application, and there are many approaches to the same problem. So, most use SQL for interacting with the database, although some have slight differences. We will be using SQLite in this course. Yes?
Does filtering through a relational database operate in linear time?
Depends on what you're doing.
Okay, and then I was going to wonder, if you're using a non-relational database, would those operations potentially be more or less efficient depending on what you're doing?
Yes, certainly. Okay, so it kind of, all right. Okay, I wish I had a chalkboard because I could just do it on the chalkboard. But, so there is there's a number of different, algorithmic approaches which will improve performance over linear time for a database application. One is the B tree. So the way, I'm kind of jumping into the middle of second year right now, but you know. So you know what a binary search tree is? Yeah. How many people have seen binary search trees? Good. How many people know what a red-black tree is? So, okay. So take a binary. This is second year algorithms. Something about second year algorithms. So take a binary search tree, right? Change the nodes so that they can contain either 1 or 2 numbers, right? So if it's got 2 numbers in it, then it's got 3 child nodes rather than 2, right? This is what's known as a 2-3 tree. You can perform operations on a 2-3 tree such that it's always balanced. So it's not, you know, the problem with a binary search tree is that you could have all of the nodes line up on one branch, which means you're still operating in linear time, which is the worst case scenario for it. But with a 2-3 tree, since it's, you know, it must be balanced by construction, you're always looking at a logarithmic search time for it. So there we go. But the thing that's interesting about a 2-3 tree is that you have, you know, basically the 2 numbers designate a bound, right? So you've got greater than, less than, or in the middle of these numbers, right? Now, imagine you had n nodes instead of 3 nodes, right? So you would have basically an array where each, like the array specifies a series of ranges that are all continuous, right? And you can go down, like you can find your position in the array, go down that branch into another subarray, etc., etc. That's what a B tree is. And B trees at 5 levels, I think, can store something like 60 billion different pieces of data.
Okay.
So in theory, like it takes time to search, like it takes an amount of time to search that array for the correct spot, but once you're there, you can get to, you know, 6 billion, over 6 billion individual pieces of data with only like 5 steps.
So it's like a combination of like some linear search, but with like an emphasis on reducing the range that you can search in.
Well, actually, it's not even linear search because the numbers inside of the B tree array are also in order, so you can binary search on them, right? So it's a logarithmic search inside of the B tree array, and then you have like a logarithmic number with a very large logarithm base for the number of levels in the tree, and that's like the type of algorithmic trickery that they use. Yeah.
That data structure would, like if you're specifying ranges, it'd be really easy to search if the data that you're filtering by is the parameters of the search. But so if you have like numbers or whatever, like the IDs of movies or something.
Yes.
You could really quickly search the IDs of movies, but if you're searching by like the title or something, then how would you search using that kind of data structure?
Well, you can search, like, so the question is, like, what your question boils down to is, how do we determine whether strings are orderable? Like, how do we determine string ordering, right? Because if it's orderable, then we can just use the same approach. Well, yeah?
I was gonna say, the way databases do that is index. So you specify to create an index on a column, so like on the ID column, and then it makes a B tree for that specific searching on that column. So searching off movie ID, but if you're gonna search based off the title, you make an index for title. And then it does its back-end nonsense stuff.
But you have to have a different index for every kind of filter that you want to apply to the data structure. Or if you want to the second word of the genre or something.
Yeah, and we're going to see searches like that. Like, routine searches are faster than than the more specialized searches, right? Yes. Sorry, speak up.
What kind of program would website databases use?
What kind of program would website databases use? Well, they would use something like oh, come on. Something like PostgreSQL, or MariaDB or MySQL. Those are the types of things that you would use on a server. Which? Oh, I don't know. I'm not familiar with it. Well, yeah, you know. So yeah, they managed to do it efficiently. Like, one of the things that you'll find is like keeping, so strings are long and clunky and take up a lot of space, and you know, indexing them is perhaps not, like comparing strings directly is expensive. So one of the things, like you might find if you were designing such software, creating a ID number corresponding to the strings such that those ID numbers remain like sorted when you add more data, you know, so the ID numbers are sorted by the same sort that the strings are. That would be an extreme, like that would be, you would be spending a small amount of data to get a huge amount of runtime, right? And that's algorithms in a nutshell, is you all, like, if you can spend a small amount of memory to get a huge amount of runtime, you take that deal pretty much every time, right? So, yeah, makes sense. Any other questions? Yeah. Oh, I teased you guys about red-black trees, but I didn't actually say what they were. So 2-3 trees, right? You take a 2-3 tree, you break it back into single nodes, but any node which has 2 values in it are now linked by a red connection, and everything else is a black connection. And that's what a red-black tree is. So rather than having perfect balance in terms of its in number of children in every branch of the tree, you're now talking about perfect black balance, where if you count only the black links, the tree is still balanced. It's still not like perfectly balanced because of the existence of red links, but it's much better than the than, you know, just a regular binary search tree. It doesn't have the same worst case scenario, and you avoid the problem of having to have 2 different types of nodes. It's simpler and therefore faster. Make sense? Cool. All right, get out of here.